Hello and welcome to Chapter 12. We're going to talk about alcohols and phenols and some important reactions, a few mechanisms, but of course we're going to start off with the functional group itself and some nomenclature. Alcohols possess what's called a hydroxyl group, right? So that OH is a hydroxyl, and then an alcohol is when you have the ROH. So it's going to impart something to that name. Like you see when it's all single bonds, you have ANE, a double bond gives you the ene, and a triple bond gives you ine. If the alcohol is the highest priority functional group, it will give you an OL suffix. So you see the ethanol and cyclopentanol examples here. You'll even see it in some of the larger and more common names like grandisol and chloramphenicol. It's a very common functional group. It's found all over the place, hence the random examples like the sex pheromone of the male boll weevil. Right? You see it in lots of natural compounds, lots of pharmaceutical compounds. Alcohol is a common functional group, hence we have a whole chapter on it. Now, you're going to see the same rules for nomenclature here that you've seen in the past, and that's going to be find the parent, right? Give the numbers, name the substituents, and then organize, right? The main thing here is alcohol is going to be the highest priority functional group that you have learned so far. So you want the longest chain that has the alcohol in it. So it may not be the longest chain overall, but the longest one with the alcohol in it. And then you're going to use that alkane nomenclature, but you're going to drop just the E and add OL. So for instance, right, butane, we put an alcohol on it, becomes butanol. You're going to number to give the OH the lowest numbering possible. So in this case, this would be a 1-butanol. You can do similar to what you guys saw with alkenes and alkynes. You can put the 1 in the name right before the OL, or it can go out in front of the parent. Either way, but you do need to number it. Now, let's see. Here's a couple more examples, right? Pentane becomes pentanol. Here, longest continuous chain would be the octane, but now if there's an alcohol, it needs to be part of the parent, and so the parent becomes hexanol. So in this case, it would be 1, 2, right? So it would be 2 propyl, 1 hexanol. If there is an alkene, right, remember you're only dropping the E. So double and triple bonds are kind of sneaky in terms of functional groups because they work their way into the parent name no matter what, even if they're not the highest priority. So for instance, when we are, let's say now we're going into naming substituents and numbering. Right, so here we go. So if we are naming this guy here, it's important that we give the lowest numbering possible to the alcohol, even though there's other substituents, and then continue on. 5. Now, that's a 6. 7. We want to go through the double bond to make this naming easier, right? Put that double bond in the parent. So this is going to be based on heptene, and so it'll be a heptenol. So now that we've got the double bond and we've got the OL, you will see me adopt more of this structure, kind of like when we had the ene-ines, where I put the numbers right in the parent so it's not ambiguous. So let's name this whole thing. We've got 1, 2, 3 methyl groups. So we're going to say 5, 5, 6, trimethyl hept 6-ene 2-ol. Right? The more interesting and complicated structures get, the more the names just roll off the tongue, right? Just beautiful, beautiful names. But they're very descriptive, and you know everything you need to draw this structure. So there's just the example of the ways you can put the numbers. If you've got a cyclic structure, right, nothing changes there except you know it's going to be on carbon 1 because you can number in any direction. Now, if it does make a difference, you could use something like alphabet to break a tie. All right, so whether I go right or left around this circle, I'm going to get something on the 3 and the 5 position. I'm going to put the bromo in the 3 position since there's nothing else to break the tie but the alphabet there. This would be a 3 bromo, 5 chloro, cyclohexanol. But again, nothing was there to be a tiebreaker except the alphabet. So what if I did an isomer like this? Now, the tiebreaker is just to give the lowest numbering possible. So now I would go counterclockwise here because I'd rather have a 2 and a 4 than a 4 and a 6. Right? So alphabet is last. So this one would be 4 bromo. I'm still going to write it down alphabetically. 2 chloro, cyclohexanol. And you could put the 1 in there, but you don't have to when it's a ring. Some common names for alcohols here. You don't have to memorize them, but something to recognize because you come across it in labs a lot. Instead of ethanol, right, that's the IUPAC name. And so there's ethanol. The common name would be ethyl alcohol. So you treat that R group like it's a substituent and then just say the word alcohol. So if you know what an isopropyl group is, then isopropyl alcohol makes more sense. Same for tert-butyl alcohol. Benzyl alcohol, you'll come across this more in organic too. A benzyl group is a benzene ring and that CH2 right there. That's important. You're still expected to be able to do RNS. So in this example here, if you want to get full credit when you are shown that 3D information, you should include R. This is an R3,3 dimethyl because, again, we're starting where the oxygen is, or the carbon with the alcohol, and we're going to give the lowest numbering after that to the 2 methyl groups. So it's 3,3 dimethyl cyclopentanol. The RNS will come up on every exam from me. It may not be worth a lot of points, but if you want all the points, you will need to be able to show that. When we talk about alcohols, we use terms like primary, secondary, and tertiary. It's similar to when we talked about primary and secondary and tertiary carbocations. The alcohol only forms one bond. So when you say primary alcohol, you're talking about the carbon that the alcohol is attached to. A primary alcohol is on a carbon with 1 R group and 2 hydrogens. Secondary, there's 2 R groups, and tertiary, there's 3. This is going to be important in our discussion because reactivity on primary and secondary might be different than that of tertiary, kind of like with the alkyl halides. When an alcohol is attached directly to a benzene ring, it is called a phenol. Again, that's nomenclature you'll get in organic too, but it's a very common structure, so it's nice to know what the word phenol means. There's always going to be a section on commercially important versions of that functional group. And so there's a few slides here on some important alcohols. They tend to be the simplest ones. Methanol is the smallest, simplest alcohol. And we use it in synthesis. We use it industrially. It's used as solvents for a lot of things. I know it's used in some dry cleaning processes. It's also used as fuel. It is poisonous. Most alcohols, or especially small alcohols, are. Ethanol is also poisonous. It's just not as poisonous, right? When it's called intoxicated because it's toxic. It's made for a number of other things besides human consumption. It's a solvent. We use it in synthesis. It's a fuel. Something that is important to know, and I'm not going to test you on this, but it would be irresponsible for me to have students go through organic and not know what denatured ethanol is. Denatured ethanol means that it has an additive to make it toxic. So if you went into the lab and you drank the ethanol in the lab, there would be something added to it, like kerosene or methanol or a couple of other things that could be added that make it not fit for human consumption. That allows us to purchase ethanol for synthesis or for lab or for solvents, avoiding taxes. If you were going to sell ethanol for human consumption, then it's going to be heavily taxed, but it will be safer for people to drink. So if you ever see denatured alcohol, this is not something for human consumption. It's like purposely made not for human consumption, right? So we do not want to mess with consuming any denatured alcohol. Isopropanol is another one's which is isopropyl alcohol. It's very common. You might have some in your bathroom at home, right? It's rubbing alcohol. It's used as an antiseptic, as a solvent. It's in gasoline, right? Lots of different uses. So those are just some common commercially available and important alcohols. When we think about physical properties of an alcohol, no surprise here because it can hydrogen bond. You're going to see the effects of the ability to hydrogen bond. You're going to see much higher boiling points compared to other compounds of similar sizes. As you get the smallest alcohols are actually going to be miscible with water. Methanol, ethanol, propanol are all pretty easily mixed with water. As you start to get longer and longer carbon chains, then it becomes more hydrophobic than hydrophilic, and it won't mix with water, so it just depends on the alcohol you're using. There's all sorts of fun properties, and we're gonna keep moving here. Alcohols are ubiquitous, so you see them all over the place, and they're involved in a lot of different processes. The acidity of alcohols and phenols. They are certainly more acidic than a CH would be typically, but they're not acids. So to deprotonate them, you often need a very strong base. Something like NaH to deprotonate an alcohol, you need a very strong base. So something stronger than we've seen so far. Hydroxide is not typically going to be strong enough. There will be an equilibrium. So if you want to really deprotonate an alcohol, NaH is a good choice. One of the reasons is hydride's a very strong base, but it also keeps you from going in the reverse because once it reacts, you make H2 and it leaves as a gas. And if you take product out, you're not going to go in the reverse direction towards starting materials. You can also use an alkali metal like sodium, lithium, or potassium. That also works. What you'll see from me most frequently is NaH. So you can see where it falls in terms of stability and how acidic it would be when you compare it to other second row elements. Right, and it makes sense here. The acidity is between the NH2 and then the halogens. Very acidic over here, not very acidic at all on this side. And hydroxides are somewhere in between. Now, there are factors that can make an alcohol more acidic, right? You remember ARIO. Now, the A, we're dealing with alcohol, so we're dealing with oxygen, but something like resonance can really affect pKa, right? So you see phenol is much more acidic than cyclohexanol. Induction affects things. This is all just review from chapter 3. Solvent effects, so sterics can affect things, but you notice it's a much smaller difference. And there's just your solvent effects. Now, how can we prepare? So in these chapters, as you move through this book, you're introduced to a functional group, you get the naming, you talk a little bit about properties and availability in the world, and then you talk about preparation, and then you move on to what can I do with an alcohol. So the preparation, a lot of these reactions are going to be review, right? We learned several ways to make an alcohol. We know that we can go substitution, right? Where we take an alkyl halide and we treat with either sodium hydroxide or water, right? Depending on if we're going to do SN2 or SN1, that can give us an alcohol. Right, that's all chapter 7 review right there. We also know that there's addition reactions. Right, we can make alcohols across double bonds in 3 ways. Right, we can do H2SO4 and water. Right, acid catalyzed hydration. You can do oxymercuration, demercuration. Both of these will give you a Markovnikov addition. Oxymercuration, demercuration would avoid carbocations, so it would avoid a rearrangement. And if you want to do anti-mark, you have hydroboration oxidation. Right? So you've got several choices on how you can make alcohols, and you have regioselectivity. A third way to prepare is going to be new. So preparation, substitution was review from chapter 7. Addition is review from chapter 8. Reduction is going to be new. So your reducing agents, you're going to need to keep track of, right? You're going to be reducing. Okay, so something to talk about when we say oxidation and reduction in organic. Oxidation and reduction, it means the same thing as it did in Gen Chem. It has to do with losing and gaining electrons. But these are all covalently bound, and so it has to do with losing ownership through the sigma bond, right? And so having electronegative or more electron withdrawing versus donating atoms is going to change the oxidation state. It's not going again, it's not going against anything from Gen Chem. You could figure out the formal charge on all of your atoms and keep track of the oxidation states. But in general, what we see with organics, increasing bonds to oxygen is going to be an oxidation, right? You're going to have a loss of electron density because the oxygen is pulling it away. A reduction is going to be less bonds to oxygen or more bonds to hydrogen. All right, so we use oxidation and reduction a lot, but it's a little bit more simple with organic because we're dealing with so many fewer elements. All right, I'm not going to ask you to calculate formal charge. All right, but if we compared these carbons as we go from left to right, it is becoming more and more oxidized. So you see the carbon goes from no bonds to oxygen to 1, 2, 3, and 4. Now going in the other direction would be reduction. All right, reduction would be going 4, 3, 4, 3, 2, 1, 0. The oxidation state's decreasing. All right, now from reduction, we need a carbonyl. Right, so 2 bonds to oxygen being reduced to 1 bond to oxygen. So we're going to have some sort of carbonyl compound giving us an alcohol compound. So what are we doing? We're adding H across the bond. We're adding H2 across the bond. Catalytic hydrogenation is possible, but it is rarely used. High temperature and pressure required. So in essence, this isn't really a useful reaction. But luckily, we have some useful reactions. We have 2, to be specific. If you're dealing with an aldehyde, right, which would have an H here, or a ketone, which would have R groups on both sides, you can use sodium borohydride, and then typically there's some sort of alcohol solvent all together in one step. From there, you will either make a primary alcohol from aldehydes or a secondary alcohol from a ketone. All right, it works really nicely, good yields. It's a relatively simple reaction. You do not need to know the mechanism. It's interesting, but I will not ask you the mechanism of this particular reaction. It is not stereoselective. If you have an asymmetric ketone, you will make, and you make a chiral center, you will make both enantiomers. Now, there is a second reaction that you must know. So NABH4 works well for aldehydes and ketones. Well, sometimes you need something stronger. So if you have a carbonyl, and then this can be a mystery. This can be an aldehyde, a ketone, a carboxylic acid. It could be an ester. It could be an anhydride. It could be an amide. Or it could even be, what am I missing? An acid halide. Any of your carbonyl-containing compounds, if you treat with lithium aluminum hydride, so that's LAH or LiAlH4, there's just 2 different ways to abbreviate, followed by water. Now, the sodium borohydride was all one step. Sodium borohydride is not nearly as reactive as lithium aluminum hydride. This is 2 steps, and it has to be 2 steps. This is dangerous if you put them together. Water and LAH do not like each other. But it's much, much stronger, so you can reduce anything to an alcohol. Right? So it could be any of these, and you could reduce it down to an alcohol with LAH. Actually, take amide out. You're going to reduce that. That reduces to an amine. You don't need that until organic 2. Don't worry. But those are your 2 options. Now, an aldehyde or a ketone, you can use either one. But if you have one of these guys, an acid halide, you want to reduce, you've got to go with LAH. And the structure is very, very similar. it's providing hydrogen on something that is less electronegative than hydrogen. So the hydrogen is actually able to take both of the electrons with it instead of you just taking the proton, right? It's the difference between when I say proton, right, that's H plus, versus hydride, which is H minus. And it's right there in the name. You have hydrogen with a lot of electron density. Again, not responsible for this mechanism. So you have some options here. What I would suggest is not to consider this one for reducing carbonyls. It takes a lot of heat and pressure. These are the two you need to focus on for reducing carbonyls. Notice they do not reduce the double bond. So if you wanted to reduce the double bond, you do need to use H2 and platinum or palladium. Now, you'll see here, this is now pointing out these other groups. When you do have more bonds to oxygen, like with a carboxylic acid or an ester, you do need excess LAH. I would say do not worry. Assume that you have enough LAH if I give that to you. There's not some intermediate. If we control, one mole of LAH. So I would say just assume that you have enough. And a note, I don't know if I've used this before with you guys, but if I put excess LAH, that means excess. That's just how I shorthand it. This is more of the same. Klein really likes this. It's not a bad mechanism. I'm just not asking you to know it. Okay, so you don't need to know it for aldehydes and ketones. You don't need to know it for carboxylic acids and their derivatives. You don't need to know NABH4 mechanism or LAH. We will, let's see, actually, let's finish up with diols. Diols are interesting here. It just means that you have two alcohols. You should be able to name these. If you have multiple alcohols, you use the Greek prefixes. They just happen to go inside the name instead of outside. So a propane diol. If you had 3, it would be a triol. This is just a common name, glycol, for diol. You hear that, especially like with ethylene and propylene glycol, which are antifreeze. And they can be prepared just like any other alcohol. You could reduce 2 different carbonyl groups, or you could do addition reactions in a strategic way. You can make anti and syn diols using addition reactions that you learned in Chapter 8. Chapter 8? Is it Chapter 9? I think it's Chapter 8. I could be wrong, but the addition chapter. We are going to start with this new preparation of alcohols called the Grignard in the next video. That's an exciting one, so come on back. Am I selling it? I don't know. I'll see you in part 2. Thank you.